Today, we're going to talk about vector spaces. Vector spaces sets the stage where we will play the linear algebra show. Let's give a definition. A vector space V over a field F is a set with a binary operation of addition, unary operation of taking the opposite or negative, a distinguished element zero, and we will put it with a bar to distinguish it from zero in the field, such that the following properties hold for all u, v, w in the vector space V, and all c and k in the field F. And so here are the axioms of a vector space. So 1. So for any u and v, u plus v is equal to v plus u. So this is a commutative law. And 2. U plus v plus w is the same as u plus v plus w. So this is associative law. Then next one is u plus 0 is equal to u. So this is axiom of 0. Next one is u plus the negative of u is equal to 0. So this is axiom of negative, opposite. So next axiom is c times u plus v is equal to c times u plus c times v. And 6, c plus k times u is equal to c times u plus k times u. So these are called distributive laws, and there are 2 of them. Seven. C times ku is equal to ck times u. So c and k are elements of the field, and so here we can multiply 2 elements of a field here. And the last axiom is that 1 times u is equal to u. These are the 8 axioms of a vector space, and they set a very rich environment for us and for the linear algebra. Elements of a vector space are called vectors. And in the context of a vector space, elements of a field are called scalars. So here in these axioms, u, v, and w are vectors, and so 0 with a bar is also a vector, and c and k are scalars here. So let us give some exercises. So use the axioms of a vector space to prove the following facts. 1. So if u plus v is equal to u plus w, then v is equal to w. Second exercise. -1, so this is an element of a field, times u is the same as minus u, so this is a vector opposite to u. And the third exercise is that 0 times u, so here 0 is a scalar, u is a vector, is equal to 0 vector 0. Let us give examples of vector spaces. So our first example is the vector space Rn over a field of real numbers. So here, vectors in this space are n tuples of real numbers, a1, a2, an, where ai's are real numbers. And so here we have operations, right? So we have addition, where we take a1, a2, an, so one vector, plus another n tuple, b1, b2, bn, and we add them component-wise. So we get a1 plus b1, a2 plus b2, an plus bn. Another operation is multiplication by scalars. So here, if we have a scalar c, which is a real number, and a vector a1, a2, an with n components, then the result of this, again, we multiply component-wise. So it will be c times a1, and this is a product of real numbers, c times a2, c times an. And finally, we have a distinguished element, which is a zero vector, and this is an n tuple with all components being 0. So here we defined a set of vectors, and we defined the operations of addition, multiplication by scalars, and the 0 vectors. And it's an easy exercise that all 8 axioms of a vector space will be satisfied. Our second example will be vectors on a Euclidean plane. So this is a vector space over the field of real numbers. So here, we defined vectors as directed segments on a plane, and we defined addition of these vectors, and we define multiplication of Euclidean vectors by real numbers. And there is also the concept of a zero vector. So it's a vector that connects each point to itself. And again, it is possible to verify that all axioms of a vector space will hold in this setting. And a variation of this example, so vectors in a Euclidean space, so meaning three-dimensional space. And again, so this is the field in this case is the field of real numbers. The third example is a generalization of Rn to the case of arbitrary field. So here we will talk about space Fn, where F is any field. So this space consists of n tuples A1, A2, An, but so all AIs here are elements of F and not real numbers. And we use the same formulas as here to define addition of vectors and multiplication of vectors by scalars. Right? So, but in this case, of course, the scalar is not going to be a real number, but the scalar is going to be an element of F. And so these operations will be well defined. And a zero vector is also defined in this way, since in any field we have 0. And so if we consider an n tuple of all zeros, then this is going to be a zero vector in Fn. So it is easy to check the axioms. So let's take commutativity. So what is commutativity axiom says? So it says that u plus v is equal to v plus u. And u and v are elements from this set. So they can be written, so we take u to be a1, a2, an, and v we take to be b1, b2, up to bn. Now, let's look at the left-hand side. So what is u plus v? So this is a1, a2, an, plus b1, b2, bn, and we add them component-wise, we get a1 plus b1, a2 plus b2, an plus bn. Now, if we look at the right-hand side, so here we have v plus u. So this is going to be b1, b2, up to bn, plus a1, a2, up to an. And this equals to b1 plus a1, b2 plus a2, bn plus an. But in a field, addition is commutative. So we have ai plus bi is equal to bi plus ai. So this is commutative law for addition in a field. Right, so because here the components of these n tuples are elements of a field, and for each component we can apply the axiom of a field, and from here we see so this implies that u plus v is the same as v plus u, because these two n tuples will have equal components. Here we verified commutative law for addition of vectors in Fn, and I leave it for you as an exercise to verify the 7 remaining axioms of a vector space for this Fn space. Let's take an important special case of this construction. So let's take n to be 8 and f to be z2. So then this becomes the space of bytes. So byte is an 8-bit n-tuple. Well, it's a vector with 8 components, and each component is an element of z2, so that is 0 or 1. And so then these bytes can be added. Right? So let's do an addition of 2 bytes. Say we have a byte like this, plus another byte 1 0 1 0 0 1 1 1. Right? So how do we add these 2 bytes? Well, the addition happens component-wise. In the first component, 0 plus 1, we get 1. In the second component, 1 plus 0, we get 1. Then in the third component, we have 1 plus 1, and this is addition in Z2. 1 plus 1 is equal to 0. Then in the fourth component, we have 0 plus 0, that's 0. In the fifth component, we have 1 plus 0, that's 1. In the sixth component, 1 plus 1, that's 0. In the seventh, 1 plus 1, that's 0. And in the last component, 0 plus 1 is equal to 1. So this is the addition operation for bytes. Another interesting special case is n equals 1. So in this case, we have an n-tuple with a single component. So this is just an element of a field. And so here we can say that F is a vector space over F. Right. So what we do here, so we treat elements of a field as vectors, and then we can add elements of the field. And we can multiply elements of a field by scalars. But scalars are again elements of the field, and we know that in a field we have operation of multiplication. And the 0 vector here is just the 0 element of a field. And again, either we can refer to this construction or verify directly that all 8 axioms of a field will hold here. So in particular, so R is real numbers, is a vector space over the field of real numbers. But we can also do an interesting twist on this, and we can say that R is a vector space over the field F, not of real numbers, but rational numbers. So here vectors are real numbers, and we can add them and we can multiply them by scalars. And scalars in this context will be rational number. So we can multiply real numbers by rational numbers. So this will be scalar multiplication. And here we have 0 vector is the 0 real number. So we can view real numbers as a vector space over rational numbers. And then in these interpretations, so real numbers become vectors. Our next example is the space of polynomials with real coefficients. So in this case, V is R of X. Right? So these are polynomials in variable X with real coefficients. And this is a vector space over the field of real numbers. And so here we treat polynomials as vectors, and we treat real numbers as scalars. And we have the following operations. We can take two polynomials and add them together. So the result will be another polynomial. So this is addition of vectors. And we can multiply a vector by a scalar. So we take any polynomial, we can multiply it by a real number, then we get another vector. And we have a 0 vector, so this will be 0 polynomial. And again, I leave it as an exercise to verify that all 8 axioms of a vector space will hold in this context. And again, we can generalize this. So we can take V to be f of x. So these are polynomials with coefficients in a field F. And this will be a vector space over F. And here, again, vectors are polynomials with coefficients in F, and scalars are elements of F. So here we can add two vectors, so the sum of two polynomials will be a polynomial, and we can take and multiply a polynomial by a scalar from F. As an example, let's consider V to be the space of polynomials over Z3. And let's just take as an example, so U will be 2x cubed plus x plus 2. So this is a polynomial, and the coefficients here are remainders from Z3. So these are 0, 1, or 2. And V is going to be x squared plus 2x plus 2. Now, what is U plus V? What's the sum of these two vectors? So here we add these polynomials. Now, the cubic term here will be 2x cubed. So quadratic term will be x squared. Now, linear term will be x plus 2x. But 1 plus 2 is equal to 0 in Z3. So this means that linear term will disappear. And for the constant term, we have 2 plus 2. But 2 plus 2 is equal to 4, which has a remainder of 1. So this means that this will be 1. So this is how we add two polynomials or two vectors in this space. In a similar fashion, we can multiply vectors by scalars here. So if we take C to be 2, so this is a scalar from Z3, then 2 times V is going to be 2 times the polynomial x squared plus 2x plus 2. And the result will be 2x squared. And then 2 times 2, that's 4, but in Z3 this is 1. So this will be x. And again, 2 times 2 is equal to 1. So we get plus 1. So this is how multiplication by scalars works in this context. Our next example of a vector space has origins in mathematical analysis. So here we take V to be functions on a real line. So here V will be the set of all functions with a real argument and assuming values in real numbers. So for example, so f of x, which is 2 to the power x, right? So this will be one of the vectors in the space V. And so here in this set, so we treat functions as vectors, and the addition of functions becomes addition of vectors. And so this is a vector space. So this is a vector space over the field of real numbers. So here in this context, scalars are real numbers, and we can multiply any function by a real scalar. And again, it's instructive to verify that all 8 axioms of a vector space will hold here. So this interpretation of functions as vectors is extremely useful, and it's kind of the right sort of a concept if you do digital signal processing. So in digital signal processing, functions are treated as vectors. And a lot of operations in digital signal processing happen, so we use the tools of linear algebra to work with functions. The next example is closer to linear algebra. So here we have V to be the space of M by N matrices with entries in a field F. So this vector space is denoted as M, Mn of F. So the elements of this vector space are, or the vectors are M by N matrices with entries in F. And this is a vector space over F. So the point here is that we can add matrices and we can multiply matrices by scalars. So let's see an example how we can do it. So so let's take F to be real numbers and consider V to be 2 by 2 matrices, M to 2 over R. Right, and so then if we have 2 matrices, 1, 2, 3, 4, and -1, 3, 0, 1, then we add matrices component-wise. So 1 plus -1, that's 0, 2 plus 3, that's 5, 3 plus 0, that's 3, and 4 plus 1, that's 5. So this is how we define the sum of 2 matrices. And we can multiply matrices by scalars. So if I have 2 times 1, 2, 3, 4, then this is 2, 4, 6, 8. And finally, we have a 0 vector here in this space. So this will be a 2 by 2 matrix with all 0 entries. And the last example that I want to mention today is something that's called 0 vector space. So this, as a set, consists of only one vector. So we have a 0 vector, right? So this is over a field F, where F can be an arbitrary field. And so here we claim that this is a vector space. So we have addition, like 0 plus 0 is equal to 0, right? So this means that there is only one vector and we can add it to itself. And we can also multiply this vector by any scalar. And the result is, when we multiply 0 vector by any scalar, the result is 0 vector. And one can formally verify that the axioms of a vector space will hold here. So geometrically, one can think of this vector space as a single point.